All right, open up your book to section 6-6. We're on page 314 in your book, and the title of this section is Inverse Circular Relations. That is, given y, find x. That's what it means to work with inverses. If you know the output, can you find the input? So the objective here is given the equation of a circular function or a trig function and a particular value of y. So you know the output. Find the specified values of x or theta graphically, numerically, and algebraically. Graphically and numerically won't be as difficult as doing it algebraically. That's what we're definitely going to find. Let's start with an example. Page 314. They give us this example here that we want to find all solutions to the equation cosine of x is equal to 0.3. Find all solutions to this. Well, we know a method to be able to find one solution, but we want to find all solutions. So what exactly does it mean when it says that they're looking for all solutions? Why is there more than one? Well, take a look at this graph of cosine of x. And let's graph along with it the horizontal line, y equals 0.3, which would be somewhere about right here, we'll say. We'll mark that as 0.3 right here. You can see that the cosine of x and y equals 0.3 intersect each other a number of times. In fact, it's an infinite number of times. There's two solutions there. Here's two intersections or solutions there. Here's two more here. It looks like these keep repeating, right? That's what it means to be periodic. The fact that cosine is periodic means it's going to repeat itself at regular intervals, which means that I'm going to have an infinite number of solutions here. So the question then becomes, well, how do I find all of these solutions? Well, we have a technique to come up with one solution. Let's see if we can use that to help us come up with all of them. Let's start out by writing out our equation that they've given us here. They told us that the cosine of x is equal to 0.3. And from what we saw in the previous chapter, we know how to solve this. That if I have cosine of x is equal to 0.3, I can use the inverse trig function to write this as x equals the cosine inverse of 0.3. Now, the problem that I have here is that this only gives me one solution. That's why it's called the inverse trig function. There's one output for this. I guess first of all the question is, well, which output are we going to get? Well, we might have to go back a little bit further and remember back into chapter 5 again and remember what the range of these inverse trig functions were. The range of cosine inverse, we wrote it in degrees back in chapter 5, but now that we know radians, and since this is in terms of x, we're in radians here. The range of this function is between 0 and 180 degrees, but that would be 0 to pi radians. So I'm going to write it that way, that the cosine inverse of 0.3 is going to be between 0 and pi. It doesn't matter what you're finding the cosine of inverse of. The result is always going to be between 0 and pi. So where does that fall on our graph? For the x is our cosine inverse value, so where is x between 0 and pi? Well, 0, of course, is right here. And this is where pi is at. It's halfway through our period. We know the period of this function is 2 pi. So pi is halfway through there. So we know the solution we're going to find is between 0 and pi. Let's mark that here. That we'll say this is right here at 0. This is right here at pi. Our solution is going to fall somewhere in this interval. That's what this tells us here. Oh, well, right here's the one solution then, right? Sitting right there in that interval from 0 to pi. Whenever you calculate the cosine inverse of a number, no matter what value I'm setting this equal to, I'm going to be finding the solution that falls right here between 0 and pi. So that right there, in fact, is the cosine inverse of 0.3. Again, that gives me one solution. I want all the solutions. So how do I go about finding the rest of these solutions? Well, one thing you should notice here about this function, we've mentioned it before. We'll come back to this property later on, but there's symmetry across the y-axis for cosine, which means it's an even function. But because it's got symmetry across the y-axis, then if that solution over there is cosine inverse, then this one over here on the left side of the y-axis should just be the opposite of that. The opposite of cosine inverse of 0.3 should be this solution right here. In fact, if I think of this as being a positive cosine inverse and the other one on the left being negative cosine inverse, I guess that's one way I could rewrite this. This is really plus or minus the cosine inverse here. All right, that takes care of two solutions. I want to get all of them, though. Well, I guess the thing to notice here is that this is periodic. So being that it's periodic, that means that this thing is going to repeat itself at regular intervals. And in particular, if I travel from one solution here to the next one, that should be exactly one period apart. That distance there should be 2 pi. If I travel from this solution here to this one right here, that should also be 2 pi. And they should keep going, right? 2 pi later, I'll find the next two, and 2 pi after that, I'll find the next two, and so forth. So it looks like these repeat themselves every 2 pi. So it looks like I could just simply say add on multiples of 2 pi. I'll write that as 2 pi times n, where n is some integer value. And that should give me all my solutions. And in fact, we can even be a little bit more specific on what values of n to pick as to, as well as the plus or minus, as to knowing which one is which solution here. All right? This all comes down to knowing where to start, by the way, that this here has a phase displacement of 0. All right? The fact that it's just cosine of x, it's not cosine of x minus any number. So that tells me where I'm starting. That tells me that I'm starting here at 0. And if I let n be 0, that's going to give me these two solutions here. So I'm going to write that right above n equals, x equals 0, that n equals 0. That's because my phase displacement, I'm going to write that d is equal to 0 there. That tells me my starting point here is at x equals 0. And if I take a look to the left of that high point, the first solution I hit there is the negative cosine inverse. In fact, I'm just going to put a little minus sign there to remember that that's the negative cosine inverse. And if I head off to the right, then the solution I see there is a positive cosine inverse. I know that's getting a little bit crowded there with everything we got marked in there, but that's what it looks like at that first value of n there, when n is 0. If you move forward with n equal 1, that means you're moving forward one period, which means that you'd be now at this value. You'd be looking at 2 pi and looking at the solutions around it. If you look at the solution off to the left, that's going to be the negative cosine inverse solution, and the solution that you see off to the right is the positive cosine inverse solution. And if you jump forward to n equals 2, now we're moving forward to 4 pi. Should mark that on my axes here. This is at 4 pi. So with n equal to 2, that's adding 4 pi onto the end there. So I'm finding the two solutions here around 4 pi when I do this. So this is the negative cosine inverse solution. This one would be the positive cosine inverse solution. So in other words, if you were asked to find a particular solution, I want you to find this one solution. Where is it at? I should be able to actually find out what value it is by knowing the right value of n and whether to use the plus or minus using this little technique here. I should be able to come up with those. That will be part of what we need to do when we solve these algebraically. In fact, that little definition that we just came up with there to find all those solutions is the definition of the ArcCosine. That is the inverse cosine relation. Notice that we're not saying inverse cosine function here, but rather inverse cosine relation. And because of the fact that we get more than one result, more than one output from this, that's why it's not a function, it's a relationship. And we're calling it the ArcCosine. So here's what we have. If you have that the cosine of z is equal to x, then you can solve for z by saying z is the arc cosine of x. From now on, when we go to solve equations like this is how we'll write them. We won't use cosine inverse because cosine inverse is only going to give you one solution. If you want to find all solutions, then arc cosine is going to be the way to do that. And then when we get down to the end there and we're ready to find out our solution, we can replace arc cosine with what we just came up with, which was the plus or minus cosine inverse of x plus 2 pi n. So we'll use arc cosine as our way of solving these problems rather than just cosine inverse, which only gives us one solution. And again, n is some integer. N can be positive, it could be 0, or it could be negative. And that will move you forward or backwards from that phase displacement from the original equation to find all your solutions. All right, let's take a look at an example here. Look at example 1 there on page 315. It says find the first 5 positive values of arc cosine of a negative 0.3. Arc cosine of a negative 0.3. Let's write that off to the side here. In fact, I'm going to say x is equal to the arc cosine of a negative 0.3. And from that definition that we just wrote down, if I say that x is the arc cosine of a negative 0.3, that's the same as if I had said the cosine of x is equal to a negative 0.3. It looks a lot like where we started in the last example. We started out with something like this, and then we figured out how to find all these solutions. And so that's all they're saying is to rewrite this using that definition. They could have said find the first 5 positive solutions to that second equation, though, that I wrote down. Just realize there's a couple ways that you could word this. So what 5 solutions are they looking for? Well, let's sketch a negative 0.3, which would be maybe somewhere about right here, we'll say. This is a negative 0.3. Let's go ahead and mark our solutions. You will notice there's a solution over here, but again, they said the first 5 positive. That one there is going to give us a negative answer there because it's to the left of the y-axis. That's the negative x value there. So I want 1, 2, 3, 4, and 5. There's our 5 solutions that we're looking for. So the question is, well, which 5 are those? Well, let's first write down our definition that we just wrote down for what arc cosine is. So again, we have x is equal to the arc cosine of a negative 0.3, or that's plus or minus the cosine inverse of a negative 0.3 plus 2 pi n. But I want to know which values of n do I pick, and do I use the plus or minus here is what I'm going to look at. Well, again, my starting point, when I look at the original equation that we started with in terms of cosine, there was no phase displacement. It was 0. So that's my starting point. Here's where n is equal to 0, right at x equals 0. So this solution that I'd find here would be the negative cosine inverse, and this one to the right is the positive cosine inverse. I want that one. I don't want the one that's on the left. If I move forward 1 period, that would be n equals 1 here, and this would be the negative cosine inverse solution. This would be the positive cosine inverse solution. If I move forward again 1 full period, that gets me to the next high point, and here is the negative cosine inverse solution. Here's the positive cosine inverse solution. All right, so we should be able to list our solutions here then, the first 5 positive ones. Let me grab my calculator and help us do that. But now with the work I've done graphically there, that tells me which 5 I'm looking for. Grab your calculator and we'll try this out. All right, so let's try this out from the home screen here. Make sure you're in radian mode first of all, because that's what we're working in. From the home screen here, we should just be able to punch in these solutions here. So the first solution that we had marked was a negative cosine inverse, or our sketch had there, but that was a negative answer. We're not going to want that one. So start with a positive cosine inverse. In fact, maybe I'll show you that one just so you can see that's a negative answer there. If I take a negative cosine inverse of a negative 0.3 plus 2 pi And I'm going to go ahead and put in, write this as 2 pi times n, even though n is going to be 0, just so you can see the formula that we're going to use each time. We're claiming that this is that first one that you see to the left of the y-axis. I'm going to get a negative answer. I don't want that one. So we're throwing him out. The next one that I hit as I move from left to right was the positive cosine inverse, so I'll just get rid of the negative that I have there. So there we go. There's our first positive answer. Again, notice that the symmetry we have there, right? One was positive, one's negative. And now we're going to move forward to n equals 1, but I want the negative cosine inverse with n equals 1. That gets me a value of 4.4. And I want to do this again, but I want to use the positive cosine inverse with n equal 1. There's the first 3 positive answers. Let's do this 2 more times. Use the negative cosine inverse with n equal to 2. And finally, use the positive cosine inverse with n equal to 2. And there are our first, 2. Try that again. There we go. There are our first 5 positive values there. Actually, there's one in there that shouldn't have been in there. All right. Those are our 5 solutions there. I'll let you fix the one that it doesn't show there, but those are our first 5 positive solutions. All right, take a look at example 2. Example 2 asks us to do this just graphically. This says find graphically the 6 values of x for which y equals 5 for the sinusoid in figure 6.6b. So that's the figure that we've got sketched here. And we're just looking for a graphical solution. So literally, we are going to look at just this graph, and the arrows that you see that they've got marked there, we're going to try to approximate where those arrows are at. That's all we're going to do. This is the easiest of the 3 techniques that we're going to talk about graphically to solve these. So negative 1, 2, 3, 4, 5. That's at this solution right here. Looks like he's at about a negative 4.5. That's this solution right here. This one right here looks like that is at about a negative 0.5. And now these should repeat for whatever the period of this function is. Now they didn't give us the equation, so I don't know exactly what the period is, but I will eventually have to find this equation and find its period. But we'll approximate these 2 solutions now. I'll just do this in a different color so we can see those a little bit easier. So there's 5, 6, 7, 8.5 is where I'm going to claim that is approximately. And we're going to say that this one right here is at 10, 11, 12.5. And now you can probably look at the first couple of solutions and these next 2 here that we just found and come up with what the period must be, but we don't have to do that. Let's find the last 2 here. So these 2 solutions here, that looks like that's 20, 21.5. And it looks like this one right here is at 25.5. So that'd be our approximation. Graphically speaking, that is what we'd come up with. If all we are given is that graph and we have to approximate those, that's the best we can do. All right, look at example 3. Example 3 now says to find numerically the 6 values of x in the example there and show that the answers agree with those that you found graphically in example 2. So our graphical approximation in the previous problem was a good approximation, but not exact. Now we're going to try to come up with a numerical solution that will be closer to the exact answer. So the first thing we're going to have to do is come up with the equation of this sinusoid here so we can actually use our calculator to sketch the sinusoid along with the line y equals 5 and find these intersections. All right, so let's come up with our equation. Y is equal to, C is your sinusoidal axis, so I guess we got to know where our low point is and where our high point is. So it looks like our low is at 2. 16 is our high, it looks like. So it looks like the two numbers they've marked there for us are, in fact, the high and the low there. I wasn't sure if that's what they were marking there for us. But that means that our sinusoidal axis is the midpoint of those. 16 and 2 is 18. Half of that is 9. I should just mark that on our sketch here. So that's 2, 3, 4, 5, 6, 7, 8, 9 is somewhere right here. Looks like is our sinusoidal axis. That's at 9. All right. So we have 9 plus, and then from 16 to down to 2, that's 14. Half of that is 7 would be our amplitude. 9 plus 7 times the cosine of b, remember, is 2 pi divided by our period. And so what's the period of this thing? So it looks like we've got a high point here at 4 and another high point here at 17. So it looks like we've got a period of 13 is what it looks like. And that's times x minus our phase displacement, which we've got that marked at 4. So let's use that one. There we go. There's our equation of this. And we want to set this equal to a value of 5 is what they wanted us to do. All right, now we want to find the 6 solutions that they've got marked here. So let's grab our calculator and plug that into y1 and y2. All right, so let's go to your y equals menu on your calculator. We got to put in 2 functions then. Let's put our sinusoid in first. 9 plus 7 times the cosine of 2 pi divided by 13. And that's times x minus 4. And again, make sure you're in radian mode here. You should be already from the previous example, but make sure you still are. And then we're going to graph y2 is going to be y equals 5. And let's graph this in the window from the graph that they've given us there. I think they went from about -7 to about 27, I think, is what they gave us here. And a scale of 1 should be fine. And then for our y's, I do want to see the x-axis, but I think that's all I really need to see. And we'll go up to maybe 18 should be fine. All right, we'll graph that. All right, so there's our sketch of this sinusoid. And we're looking for those 6 solutions that you see here. They didn't ask us for the first, 4 positive or anything like that. They just said find those 6 solutions that they got there, unlike the first example. And so we want to find those 6 solutions, so we should be able to find the intersection. If we go to second calc, and we go to intersect, and give it your first curve, which I'll just call y1, our second curve, which is y2, and give it a guess. I know that that first solution we said was approximately back there at about negative, what was it, -4 or negative, 4.5. And we get negative 4.4915 is that first solution. In fact, let me grab a picture of that so I have that one. And then let's find the next one. Go to second calc and do an intersect. Get your 2 curves. And this one was around a negative 0.5. That's our guess. And there we go. I'll grab a picture of that. All right, so let's put those into our sketch here. Just so I have those numbers. All right, so our solutions that we've got here, we've got 2 of them. So we found that x is equal to negative 4.492, I guess, if we round that, and a negative 0.508 for the other solution. Now you could continue finding solutions like this, but it turns out that since we know the period, we could just keep adding the period onto those to find the rest of these solutions. That's another way you could go about solving for the rest of these. I'll go ahead and find the other two solutions, at least on the calculator here. So let's go back to our calculator and do that. Let's go to second calc and we'll do an intersection. Put your two curves. And the next solution was somewhere around, what, 8.5, I think we said? Yeah, 8.508. And I don't need to copy that yet. Let's find we'll find one more, and then we'll just end up adding on our period for the last two here. Give your two curves, and that solution was somewhere around 12.5. I think we said it was 12.5. Yeah, 12.49. Very nice. Let's grab a picture of that. All right, so let's copy those into our sketch here as well. All right, so we can write down our two other solutions that we just came up with. So we have x equals 8.508 and x is equal to, let's scroll down, 12.492. Again, you can keep finding solutions there on your calculator, but once you know the period, just add the period on. So if I add on 13 to the 8.5, I'm going to get 21.508. Add another 13 onto that 12.492, that's 25.492. So our approximation of these being around 21.5 and 25.5 was pretty good. In fact, if we go back to the previous example there and look at our approximations we came up with, these all seem to be very close to the actual solutions that we came up with numerically here. So those are our 6 numerical solutions. That's a graphical solution with the previous example and a numerical solution with this example. All right, and that's as far as we're going here with the first half of section 6.6.